Welcome back to my rubber heart. Today we are talking about rubber recycling technologies that have moved beyond the research phase and are commercially available. These are not just ideas being tested in a lab, they are real processes being used in factories to handle waste rubber in a way that's more sustainable and economically viable. But how do these methods work? What makes them effective? And why have they been successfully commercialized when so many other recycling technologies fail to reach that stage? That's what we are going to break down today. One of the important technologies in commercial rubber recycling is devulcanization. Rubber, especially from tires, is vulcanized to make it more durable, meaning it has sulfur crosslinks that make it strong, elastic, and resistant to degradation. The problem is, once rubber is vulcanized, it's incredibly difficult to process it again, which is why grinding all tires into chrome rubber is often the best we can do. Devulcanization aims to reverse that process by selectively breaking the sulfur crosslinks while leaving the rest of the rubber intact. This allows the rubber to regain some of its original processability so it can be used in new products. There are multiple ways to achieve devulcanization, but one of the most commercially viable approaches is the supercritical carbon dioxide method, developed by Tyromer. In this process, ground tire rubber is mixed with supercritical carbon dioxide, which is a phase of CO2 where it behaves like both a gas and a liquid. In this state, the CO2 penetrates the rubber matrix and swells it, weakening the sulfur bonds. Under controlled conditions, the sulfur crosslinks are broken, but the main polymer chain remains mostly intact. What makes this process particularly attractive is that it operates at relatively low temperatures and avoids the use of harsh chemicals, which means the rubber's properties are preserved, making it possible to incorporate the recovered material into high-quality applications like new tires. This is a major advantage over mechanical grinding, which simply reduces rubber into small particles without restoring its elasticity. Another widely used commercial rubber recycling method is pyrolysis, a thermal process that breaks down rubber into valuable byproducts like oil, gas, and carbon black. Unlike combustion, which burns rubber and releases harmful emissions, pyrolysis occurs in an oxygen-free environment, preventing complete oxidation and instead causing the long-chain polymers in rubber to break into smaller molecules. This happens inside a sealed reactor at temperatures between 400 Celsius and 600 Celsius, where the rubber decomposes into pyrolysis oil, syngas, and char. The oil can be refined into fuel or used as a feedstock for chemical production. The gas can be burned for energy, and the char contains recoverable carbon black, which can be used in new rubber compounds. This technology has been successfully commercialized by companies like Clean Industries, which has developed continuous pyrolysis reactors that can process large amounts of waste tires efficiently. What makes this process commercially viable is that it not only reduces tire waste, but also generates sellable products, making it economically attractive. Pyrolysis is often used where there's a strong demand for alternative fuels and recovered carbon black, especially in regions trying to reduce reliance on virgin materials. Another process that has reached commercial scale is micronized rubber powder, or MRP, a method that takes rubber recycling a step further by grinding rubber into ultrafine particles. Instead of just shredding rubber into chrome, which still has limited applications, MRP reduces rubber down to micron-scale particles, making it possible to blend it into plastics, coatings, asphalt, and even new rubber compounds. Companies like Lehigh Technologies have developed high-efficiency cryogenic grinding systems, where rubber is frozen using liquid nitrogen, making it brittle enough to be ground into powder without the heat damage caused by conventional mechanical grinding. Cryogenic processing is particularly useful for preserving the material's properties, as rubber tends to degrade when subjected to excessive heat during grinding. Because the final powder is so fine, it can be incorporated into new rubber and plastic products without compromising their strength and flexibility. This makes MRP one of the most effective ways to create circular economy solutions for rubber waste, reducing the need for virgin raw materials while still maintaining high performance properties. Each of these technologies, devulcanization, pyrolysis, and micronized rubber powder production, has succeeded because it provides both environmental benefits and economic value. They don't just reduce waste, they also create useful, marketable products, which is why they have been able to scale up from experimental concepts to industrial operations. These processes represent major advancements in making rubber recycling more efficient and sustainable. And as they continue to improve, they have the potential to reshape how we think about end-of-life rubber products. Thanks for turning into my rubber heart. If you found this episode insightful, don't forget to like, subscribe, and hit the bell icon to stay updated with our latest content. Let us know in the comments which of these technologies you find most interesting, or if there's other topic you would like us to explore. See you next time.